Thank you, Mr. Chairman. Good morning, everyone, and welcome to my presentation. This is the outline. After a brief introduction about the motivation of our research activity, I will describe the system architecture we propose, with a focus on the smart task manager algorithm and the mechanism of risk level detection we implemented. And then some experimental results, and finally some conclusions. Let me start with a couple of considerations. Tractor overturn is the main cause of death when an implement or trailer is connected, and most of the accidents occur due to human errors. For this reason, there is a strong need for to introduce onboard advanced control system able to enhance both the pre-crash safety and also the operator safety. The second consideration is that in agricultural environment, for example, nowadays control systems take in account only the tractor characteristics, and this is a problem because it is well known that vehicle dynamics and working condition limit of the whole machinery change in a not negligible way when an implement is connected. Moreover, almost 90% of the implements on the market have no ECU on board, and consequently they cannot communicate with tractor ECU. For this reason, we propose a solution, a complete wireless solution, able to detect the presence and to monitor the dynamics of a connected implement, and able also to communicate with the main vehicle ECU, allowing dynamical updates of the vehicle stability control parameters. The goal of the system is the detection of the dangerous working condition of the whole machinery, vehicle plus trailer or implement. And to do this, we need to calculate the relative yaw angle between the tractor and the trailer. To do this, we implemented a system composed by two devices. The first one is the wireless master device, which is mounted on directly on the tractor, and it is in charge of the complex mathematical computation of the algorithms, in particular of the yaw angles, which is needed to identify the risk level condition of the system. And the second device is the wireless end device. It is mounted on the trailer or on the implement, and is a completely standalone system. There is no connection with the main vehicle. Therefore, there is a problem with the power supply. We solved this problem including a vibrational energy harvesting system, able to get energy from the natural vibration of the system when it is on duty. But for safety reasons related to the application, we need to keep a backup battery. The power consumption constraints are very strict in this kind of application. Therefore, the classical ultra-low power design technique for the hard components are not enough, and there is a need of a more complex approach, in particular an hardware-software co-design approach. And for this reason, we implemented also a smart task manager algorithm running on the device. This is the architecture of the two implemented devices. In particular, as you can see, they share some common ultra-low power components, in particular the microcontroller, the transceiver, and the inertial sensor, which include a 3-axis magnetometer and a 3-axis accelerometer in the same chip. And substantially they differs from the power supply stage and the power management stage. When we're talking about the master device, there is no problem because it is directly connected with the vehicle battery. But there is a need for a more complex architecture when we're talking about the end device. In particular, there is a need of a smart LDO, which is able to detect if the vibration energy gathered from the harvester is enough to execute the task. If yes, okay, no problem. If no, the ultra low power connect directly the battery with the node to guarantee the correct operation. If there is a surplus of energy, of course, this can be used to recharge the battery through the battery charger. To reduce its power consumption, the end device implements a task manager exploiting a DVFS technique. The device can operate in only two states, the parking state and the active state, and the presence of or not of vibration is used to identify the state. When in parking, the device has only to check the presence of vibrations, while when in active state, the device measures acceleration and the magnetic field components and calculates the pitch and roll angles in order to detect its actual risk level condition. The risk level condition are used to change dynamically the sleeping time between two consecutive task execution. Of course, if dangerous condition is detected, the sleeping time is reduced, and vice versa. If there is no risk, the sleeping time can be increased for power saving. To detect the dangerous working condition of the whole machinery, we need also to know where a vehicle and trailer are operating. Both master and device use the measured acceleration to calculate their pitch and roll angles, which are used to detect the respective risk level condition, as I said before. While the relative U angle identification requires a complex mathematical computation, and therefore, to save power, the end device sends the measured acceleration and the magnetic field components to the master, which calculate all the U angles. When we have the U angles, we have all the information needed to detect if the vehicle and trailer are moving on the same plane, tilted or not, or if they are moving on a different planes. Of course, depending on the connected implement or trailer, we can define different warning thresholds for safe working condition of the whole machinery. In this slide shows experimental results about the characterization of the vibrational energy harvester implemented. The transducer is a commercial piezoelectric transducer, and it has been tuned to obtain a resonance frequency of 112 Hz, which is the one measured on a real case study of an A-Baler. As you can see, output power range is from a few tenths of microwatt to several hundreds of microwatt, depending on the acceleration strength. with an efficiency which is up to 86%. Of course, output power and efficiency drop when low vibration occur, because the generated power is small and most of it is used to supply the front-end electronics of the harvester. This slide shows the measured power consumption of the end device when in active state and in parking state for different sleeping time interval. You can see that the power consumption is strictly dependent on the sleeping time, and the optimum sleeping time is chosen automatically from the task manager, considering both the actual risk level condition and available power from the harvester. In particular, where no or low energy are available from the harvester, the task manager chooses sleeping time with higher granularity for power saving. Finally, we have presented a wireless sensor system able to improve the pre-crash safety system in vehicles. In particular, thanks to its capability to detect dynamical dangerous working condition concerning the whole machinery. Moreover, the need for battery replacement of the end device has been eliminated thanks to the hardware software co-design approach, which led to the implementation of a customized vibrational energy harvester and also a smart task manager algorithm. Okay, thank you.